Hello everyone. Good afternoon. Thank you so much for your patience and your time. So welcome to Efficient Energy's webinar series. My name is Nikhil Gadge. I am from marketing, and our today's topic is protection device withstand duty and short circuit in data center and mission critical facilities. So Q&A is open. We will run live polls during the session also. So stay engaged. Today, with us, we have two industry experts as panelists who will guide us throughout the session, Mr. Prasad Gore and Mr. Rajan Mehta. So, Mr. Rajan Mehta, he is CEO at Efficient Energy Consulting Private Limited. For he has experience of more than 24 plus of years in power quality, reliability, electrical network optimizations. He is chartered electrical engineer and part of National Standard Building Committee as well. He has written numerous standards, including IS 17036. He has worked with 2 megawatt to 150 megawatt of DC projects across India and in US throughout the project lifecycle from design stage till expansion. Also, he has led 200 plus advanced power system studies like voltage stability, harmonics, arc flash, all the power system related studies across India. He executed testing and commissioning projects for more than 300 megawatt of greenfield data centers. Also, he is an expert in L1 to L5 complete MEP management. So, over to you, Rajan sir.
A very warm welcome and good afternoon, good morning for someone which I'm seeing out of India. Thank you for joining us. We will try and like this is our second in this series, and I have with me Prasad, my colleague, who brings a vast experience and a very deep domain knowledge in this very mission critical subject, I would say, of protective device coordination. And while the topic does talk about data centers, but I believe this equally applies to any mission critical facility, be it oil and gas, be it infrastructure, metros, and many different types of verticals. So, having said that, and having with me Prasad, we are glad to continue this series, the second in this series of protective device coordination, and we hope to bring the whole purpose of doing this series was, to dispel a lot of myths which do exist around these studies in the market, in industry, as well as open up certain I would say not easily available references, not easily available guidelines, thumb rules, definitions, ways and means to do these studies, which a Google or a chat GPT for that matter today is not able to provide. Going beyond what is important, and through our lens of practical experiences that we have been experiencing doing more than 1 gigawatt of studies across various domains. So this is part two in the series that we are targeting today. Um, yeah. So our today's topic, right, short circuit study and device duty of protection devices. That's part two of this series. And why is this important for the topic of protective device coordination? So the first and foremost is why is short circuit study necessary before you go and conduct a power protective device coordination study, right? That there are few key aspects why it is essential. First and foremost, you need to ensure that you have the right available short circuit currents throughout your network, right, throughout the power system, before you can actually even go and do your protective device coordination. Next is your equipment withstand capabilities. Those are very important. Your bus bars, your transformers, your cables, your switch gear, and so on and so forth. Then, most important for protective device coordination is your coordination selectivity. It all depends on understanding the fault currents in your proper with respect to proper trip settings, time delays, etc., and not to mention safety, reliability of the systems, and thus to arrive at an optimized device selection and settings. Now that's as far as the short circuit study is concerned. There is also this device duty, right, which is a very important part and which kind of is going to be the focus of our session today, along with short circuit. That how much and how often is your productive device expected to operate under certain conditions in the electrical system? That is what essentially we're talking about device duty. So it is, if I would say, device duty is like the workload or the stress that your devices will experience, and it must be known and matched to your device's capabilities to ensure a safe and reliable operation. So that is the essence why we are covering this important topic of short circuit study and device duty of protection devices in this 5-part series of protective device coordination. You'll have to bear with us because we are going to get a little classroom level topics to give you guys a better understanding of what goes and what is the behind the curtain scenes that go on to do a protected device coordination. Anybody and everybody can do with an ETAP today is what it seems, but that's one myth I think we are going to be dispelling today with Prasad here leading the show. Having said that, so the first what we are going to do is we are trying to present you one case, okay, with respect to, if you can look at this. So in the first series we had explained on the time current coordination curves, TCC curve we had familiarized you with, right? So now we are trying to show you a typical case which you can have a look at. Can you bring it on the screen? The case. Yeah. So this is your question one for today. As usual, we are going to be bombarding you with polls so that we know that you're not sleeping out there and engaging with us, interacting with us. So this question, is there on your screen, we want you to answer, and that poll, I guess, will come on your screen also. We want you to answer that, is the TCC that you can see correct with respect to selectivity, considering that the loading, etc., everything has been taken care of. Okay, so you can move around the poll question to see at the TCC if you want to. Look at the TCC, time current coordination curve. There are two breakers. One is a 630 ampere, one is a 400 ampere breaker. And we want you to answer the question whether this TCC is correct with respect to selectivity, considering the loading is already being taken care of. What do you think? Is it a yes? Is it a no? Or if you're not sure, would love to have your opinions on this. Okay, so we have about a lot of people are voting for one particular answer. Some, okay, a large majority are saying you need more information. Okay, I'll wait for some more people to vote in. So look at the TCC, right? A typical TCC, what you will look at, does it seem coordinated? Does it seem to offer selectivity? Okay. So I think a lot of you have said that you need more information. Fair enough. That's a fair, I think we can close the poll. That's, I think, the most voted answer is 57% of you have said that you need more information. The second is that, yes, the curve is, the TCC does demonstrate selectivity. So I think this is the first myth that we are going to be busting, that why this TCC is not having the right selectivity. And I'll invite Prasad to take over and explain in detail. And this case study is going to form the basis of our today's webinar. The reason why we need to deep dive into device duty and short circuit is going to be one of the reasons, one of the basis is going to be this case study. And just before I hand it over to Prasad, I would also like to say is that this topic of productive device coordination is really, really vast. And to cover all the nuances of this in an 1 hour webinar is really difficult. So for us also, it's really challenging to really decide on what type of content to be presenting, what type of content will make sense, will make meaning to you. At the same time, not making it so trivial that you can go and do a chat GPT or something like that and get the answers for yourself. So that's the balance that we're trying to arrive. And you have in your screen the answer, which Prasad will walk you through. Thanks, Prasad.
Yeah, thank you very much, Rajan sir and Nikhil. Uh, okay, now seeing the topic, you must have come across like we are going to talk about only about the protection device duties. Is this important for you to know the device duty before you actually do and carry out the coordination? So with this, one second. Okay.
He wanted all of you to see his handsome face.
Okay, fine. Yeah. So basically, this TCC coordination is wrong, and most of you rightly said that you need to have more information. And here, the information is that here the breaker itself does not allow the instantaneous trip. So you must have come across this kind of PCC in your relay coordination, wherein the ETAP basically allows the instantaneous element to disable. If you go and check the ETAP has a we have the possibility that we can make it instantaneous and the curves look like this. But ETAP basically they are a PDC module, that is protection device module, star module. It is not concerned with the device duty of the breakers. They are not having the information whether there is a right device duty is selected for to have the instantaneous disable. So here we are going to answer this question whether and how the device duty will matter the most if for the enablement or disablement of the instantaneous element. Okay, so what we are covering today is the terms used in a short circuit study, then understanding of short circuit equation, understanding of device duty. Obviously, this is the main topic today of today's webinar. Okay, now understanding the device duty, you all are familiar with ICS. What is ICS? What is ICU? Most of us have seen all these values given on the breaker itself, the frame of the breaker itself. So we are not going much deep into the definition in a regular way. So before going to the definitions and what is exactly all these parameters are, we'll have one more question, poll question, which is on your screen. Does ICU include a DC component? So are you aware of this? Whether the ICU, which we say 50 kiloampere or let's say 36 kiloampere, so this ICU does it account for a DC component?
We're going back to basics, to our school, college books.
Yeah. So if you know this, then you definitely know what does ICU exactly mean.
We have some more participants to go. Okay, I think, yeah, we can close the poll. Most voted answer is no.
Okay. So basically, how many are there? Like
Yeah,
44.
45% of people have voted for no.
So basically, so that this means you better understand the ICU.
You want
So
to say the right answer?
yeah. So ICU DC component is not included. Basically, we have two different nomenclature for that. One is ICU symmetrical and one is ICU asymmetrical. So there are two cases wherein we have to look into both the cases basically. But what we have on the frame given, that is a symmetrical value. So symmetrical value is not including any DC component, but asymmetrical value will have the DC component included. Okay, so we'll go through the IC definitions. What IC says about this ICS, ICU, ICW, ICM, IPIC. Basically, IPIC gives in the HV breakers. But all these terms, if I have to tell you, these terms are defined by the manufacturers basically, and there is no hard and fast rule that this ICS should be like this, ICU should be like this. That completely depends on the manufacturing process, the material that has been used, the contacts material that has been used, the frame size and its insulation category that has been used, that is decide the ICU ICS. So what IC says about these definitions, then we'll look into this. ICM, that is rated short circuit making capacity. So if you see all this definition, it is assigned to. So if you see, this word will be there, assigned to the circuit breaker by the manufacturer. So IC is not saying that this should be like this should be like this, but IC says you assign some value, some capacity to your breaker, and after that, at a specified power factor again, and after that, we will see whether your breaker is complying to this whatever assigned capacity is there, that will be complying on. Are you complying on? So basically, even in the last webinar, we explained that IC has this kind of circuit, short circuit, is having this kind of short circuit test bench where the breaker, they select the breaker and the breaker is tested at this. This will have some certain power factor. So specified power factor is given. So at specified power factor, if you know in detail, normally 0.2 power factor is taken for the this kind of testing. The operational voltage, rated frequency, everything is specified by the IEC, and the manufacturer has to see the capacity they have given is tested at IEC labs. Okay, so basically this is having the DC, and it is expressed as maximum prospective peak. I will explain you in further slides what exactly this means, but this is the definition. So definition says it is just some assigned value by the manufacturer. Again, we are having short circuit breaking capacity. That is breaking capacity, that is IB. The rated short circuit breaking capacity again of the circuit breakers are the values of the short circuit breaking capacity assigned to the circuit breaker by the manufacturer for rated operational voltage under specified condition. A rated short circuit breaking capacity requires that the circuit breaker shall be able to break any value of a short circuit current up to and including the value corresponding to the rated capacity at given power frequency recovery voltage. Now recovery voltage, we again, this was explained to you in the last webinar. So that recovery voltage is much more important when the breaker is actually opening or breaking the short circuit current. Then again the same prescribed test voltage values. So test voltage values can be anything, because if you can see, all the labs may not have 440 volt setup, they might have 230 volt setup. So the manufacturer gives all the values for all the voltages. So if you can see in the data sheet, even from 230 volts, it starts from 440 and it goes up to 690 volts. So 690 volts, 55 kiloampere, this kind of combination also you can see. That again depends on the test bench that the particular lab is having. So they can have a different voltage, and the manufacturer has to give the value for that particular voltage levels. Then it's rated ultimate short circuit breaking capacity. Now we have seen what is short circuit breaking capacity. Now short circuit breaking capacity, we have ICU and we have ICS. So ICU means the rated ultimate short circuit breaking capacity of a circuit breaker is the value assigned to the circuit breaker by the manufacturer. Again, every definition will have the same answer. It is assigned value. So basically, it's assigned by manufacturer based on certain manufacturing processes. So again, it is express value prospective breaking current. Okay, it is in kiloampere. So we know that 50 kiloampere, 65 kiloampere, that's what we see on the breakers. Then we have ICS. Again, if you see the ICS breaking capacity assigned to the circuit breaker by manufacturer corresponding operational voltage under conditions specified in the test. So this word is basically important. How is that important, that we'll be covering in the next slide when we'll be seeing the difference between the ICU and ICS. Okay, and then we have most important term, which is rated short time withstand current. So this is very important but always overlooked. So again, this is the same thing, withstand current assigned to the circuit breaker by the manufacturer, but here you will have time delay. Short time delay associated with the rated short time withstand current shall be at least 0.05 second, and maximum you can go up to 1 second, or even in some cases you can have a 3 seconds value. Okay, now this slide, after this slide, we'll be going a little deeper to understand what is a short circuit basically means. Like we now understood what is the definition of ICS, what is the definition of ICU, everything is done, but how the test is been carried out and what exactly this ICS mean, and how does this value is confirmed by IC. Now, a manufacturer says my ICS is, let's say, 50 kiloampere, but when and how, that IC has to decide. So IC will generate some short circuit current, and based on certain test sequence, they will see what is ICS and ICU actually carried by the breakers. So you must have seen this is a very typical short circuit waveform. Initially, we have this peak current. There is asymmetry because of this DC component. Then there is a steady state.
It's not very visible. Can you make the cursor a little more visible?
Yeah. Okay. 1 second.
Yeah.
Okay. So initially, there is a DC component, obviously, and there will be a asymmetry. So this kind of waveform is there in the short circuit. So how does this waveform come, and what is the equations behind it? We must have seen it in our college days, but we will revise here once again to make you understand what exactly ICS means and what exactly ICU means. So before that, I just want to understand what do you think in short circuit study, which current is calculated? Are we calculating a instantaneous current, or RMS current, or average current?
This probably is the easiest one.
Yeah.
Or not.
Maybe. It is just to understand whether you are familiar with the waveforms, the RMS, the what is instantaneous.
There is a difference of opinion, I guess. We appreciate your participation in these polls. It allows us to curate the content and the flavor of the audience, with respect to what is your understanding. So the more people vote, the more it allows us to deep dive into any topics, maybe not deep dive, go through it faster. So participation is really encouraged as much as possible. Okay, so I think we have a good amount of people who have voted. But yeah, there is almost a tie between instantaneous and RMS.
Okay. So we are closing the poll. Okay, instantaneous, most of them is
Almost a tie.
yeah 50-50. Okay, so basically, in short circuit study, we are talking about RMS only. Even in short circuit initial symmetrical fault, we are talking about the RMS value. We are not talking about the instantaneous value, because instantaneous value is the value at the instant. So it is very difficult to know the exact value or at any instant, because why is this so? Because the fault can occur on any point on the wave. So instantaneous values are not taken for a short circuit studies. We always go for RMS studies, RMS values, and which is then uh, compared with breaking device duties, breaking currents. Okay, so with this, we are just going into to understand what this waveform, how does this waveform is formed or derived from. And as I told you, these equations you must have come across everywhere, because this is the basic differential equation for LR circuit. So this is not limited to any short circuit, but this is everywhere, wherever there is a inductive load or any inductors, reactors we are talking about, transformers we are talking about. This is the basic equation to derive the instantaneous current. Now this is instantaneous current. So all these waveforms is formed by the number of instantaneous values. So every instance there will be some current, and then we have the waveform, and then we calculate the RMS value based on the time duration that we consider. It is not always required you take a 50 hertz frequency, then you have to take 20 millisecond as a time duration. Time duration can be anything, but we always RMS over a complete cycle. So basically we take the time as 20 milliseconds. So this equation again, before this, I will just draw one circuit, which you all know. This is my favorite circuit. Okay, now this is your source and this is your source impedance. So this is now the load side situation, and here there is a fault. Now here again you have a motor connected, right? So there is a motor connected, but before motor, the fault occurs at this bus. So now this is the complete circuit. Now we have to find out what is I of t. And if we find the I of t, then we are going to find out on this particular waveform. Okay, so this is basically based on our very favorite network theorem, KVL. So this is L di by dt. This is L. This is R. This is RIT, and this is Vm sine omega t plus theta. So this is so we have to just, before that, we know we can do this differential, solve this differential equation through number of methods. We can solve this by integrating factor. We can solve this by Laplace transforms, everything what is easy is that we can solve. But for before this, we have to just convert this differential equation in this standard format. So this is basically is called first order ordinary differential equation, and we have to solve this by integrating factors. Then we go and have the solutions. This is the basically the final solutions. There are a number of methods in between that we can actually was going to present in the slide, but that was
Yes.
uh,
I think I desisted. I pursued it Prasad, to not get into a classroom. So, but anybody who's interested, we'll definitely be happy to deep dive into it later.
yeah. So I can see even the college students have joined. So we know when we have this kind of differential equation, then what we have is I of t is basically is consist of I transient, and then we have I particular solution IP. So this is basically the solution. So one part is transient and one part is the steady state. So here in the short circuit current, this particular part you will see this is a transient part, and this will decay based on this term. So this is nothing but what we say X by R. So why X by R is important in the short circuit, we'll come to know by solving this equation. And then this is your regular steady state equation where this is Vm, right? And this is your Z. So Vm divided by Z, this is basically Im sine omega t. So this is a very basic understanding of this. But how we have derived this, and that have a number of steps in between. Okay, so what we have done, we have made a Excel out of these equations, and we have plotted in XY terms. That I will just explain you now what exactly this means and what we are trying to explain here. So what we are trying to explain here is the short circuit equation. If you see whatever we are doing with this formula also, we can know what is the worst case scenario, what is the maximum fault that can occur, or what will be the maximum value of I of t that we can come across. But in reality, the fault is not always happening on the zero crossover of the voltage. Fault can occur any point on a wave. So we are going to see the effect of point on a wave on which factor, if it really affects, whether it is a transient factors or whether it is a steady state factor it is affecting. Then we will see what is the effect of X by R. So normally this is very important, because when we when we design any transformer, uh, then there is some certain X by R that we can actually go and ask for having a definite impedance of the transformer, so that the device duty of the component on the secondary side can be altered or can be reduced. Okay, and then lastly, we'll see why transient component is there. So everybody must have this question of where this DC component come from. Now, if you see this wave equation, you know this is the DC component. But how and why this is there in the circuit, that I think very few must be knowing it. Okay, then before jumping into the very mathematical session, I'm just handing over the session to Nikhil to explain you about the CEP.
Thank you so much, Prasad sir and Rajan sir. So let me just take you all up out from this deep session before our brains heat up. Let's just lighten the mood a bit. So let me quickly introduce you Efficient Energy Consulting to all of you. So founded in 2014 with the vision of reshaping the way electrical networks are managed. Efficient Energy is an award-winning independent consulting company specializing in improving reliability and efficiency of data centers and mission-critical facilities throughout the complete MEP, from design stage till the expansion stage. L1 to L5 greenfield testing and commissioning is there, design validations, power system studies, MEP risk management, audits, PU optimization, single point failure studies, and IoT solutions is also there. So in today's context, our focus, which is power system studies, comes from our hands-on experience with more than 500 facilities, including over 800 megawatt of data center capacity. Efficient Energy has delivered comprehensive electrical design validations for greenfield and brownfield sites with IT loads ranging from 2 megawatt to over 150 megawatt, both in India and internationally. And we have a team of more than 45 electrical and mechanical engineers with experience in data centers for the last 10 years in design validation studies such as load flow, protective device coordination, arc flash, harmonics, short circuit, etc. We are also working during the operational stages of more than 200 megawatt of data center capacity, where we focus on single point failure analysis, reliability studies, risk management, and efficiency studies, which allows us a holistic view of what mistakes can be rectified during the greenfield stage itself. So this is the overall view of what efficient energy consulting does. Specifically in power system studies, uh, we do short circuit analysis, load flow analysis, STLT, protective device relay coordination, transient stability studies, arc flash studies is there, harmonic analysis, advanced EMTP modeling is there, ground grid studies is there, motor interest analysis, single point failure studies, and so on. Efficient Energy is not just a service provider for all of us. We are basically partnered throughout the life cycle from for the facility from design till expansion in operation. So we have worked with top data centers, be it designing for selectivity, evaluating arc flash risk, or optimizing relays to minimize the cascading failures. Our goal is to make the electrical network more reliable, compliant, and future ready. So with that, again, let's dive into this topic and unpack what the real world nuances of protective device coordinations are there. So over to you, Rajan sir and Prasad sir.
Yeah. Okay, now we have seen what is short circuit. Basically, now we are jumping into the short circuit explanation. So now these are some terms you must have come across during your short circuit studies. So this is one is that is I double dash K. What we say I double dash K is initial symmetrical short circuit current. What is initial symmetrical short circuit current? Means it is basically when the fault is occurring and the impedance remains same at zero time value. So zero time means T0, T minus 0 and T0, T plus 0. We'll be talking in that terms. So at T0, the RMS value of AC symmetrical component. Again, this is only talking about the AC symmetrical component of the prospective short circuit current applicable at the instant of short circuit. So I will explain you through waveform what is the initial symmetrical value. Then there is a symmetrical short circuit breaking current. So now this is a breaking current. Now if you see again there will be same thing RMS of an integral cycle. Now this is basically the term used in a IC standard 60909. RMS value of integral cycle. It is very difficult to understand, but in the waveform, I'll let you know what exactly this IC means out of this. Okay, then thermal equivalent short circuit current is there, ITH. So ITH, if we are doing a lot of coordination study, short circuit study, but in many times this ITH current is not been seen what exactly this is for the breakers or for the matter of fact for the transformers or cables. We don't see much of this. We only go and see what we only go and check this particular value. What is my breaking capacity and what is my making capacity? That much only we see, and rest of things we really don't go and check. But this is what we at ECPL we carry out the short circuit study, and we include this particular component of short circuit current. So again, the name suggests this is thermal equivalent. This is completely basically depends on the I square T capacity of the equipment. Completely thermal. There is no electromechanical stresses that it accounts for. Okay, now let's understand these terms through a waveform. But before that, going into these terms, we'll be checking these terms on the waveforms. We'll be checking this equation, how we have built on the Excel, and what is exactly the effect of point on wave, X by R, and transient. So I'm just moving onto the Excel. Just give me a second for this. Okay. Now this one is the plot from that equation. So we have plotted this graph based on the equations. We have taken some time intervals here, and you can see these are the result of this. So normally in maximum we see the transformer capacity 2000 kVA or 2005 kVA. To the maximum we can see the transformer capacity up to 3200 something kVA, because the maximum current which can be which the breaker is having, I think we are having maximum of 6300 ampere circuit breaker. So with this on LV side on 415 volt system, I think the current is limited to 6300 circuit breaker. I don't know whether recently if any development has occurred, but to the my knowledge 6300 ampere is the maximum breaker. So that limits your capacity of the transformer basically. So here 2000 kVA with the regular 6.25 impedance, X by R ratio is basically in between 6 to 7 for the transformer. Now we'll see three aspects I told you that I'll be explaining you. The one is the point on the wave, what will it affect, and second one the X by R, and last one this component. This component, what is this component is, that I'll be explaining you. Okay, now if you see here the initially I have taken this as a 0. So this is basically 0. 0 means the voltage is at 0 and the fault has occurred. So in this case, this will be a typical. One second. Okay, so in this will be the typical an actual RMS waveform that we'll be getting, the green one. So green one is basically the total RMS, which consists of, as we have seen, the steady state current, that is a particular solution of that differential, and the transient part of the equation. So this is the transient part of the equation, and this is the steady state part of the equation. So at this moment, you can see the voltage is at 0, the fault is at maximum, because this is inductive in nature, so it will have a lagging nature. So this current lags behind the voltage, and here it is 90°. And at this point, there will be a transient current of this nature, and the total of this you will be getting this. Now you can see at 2000 ampere with this percentage 6.25 Z impedance, X bar of 8, we will be getting the fault current somewhere around 46 kiloampere, and the peak, which is this value, which is of interest, this is around 112 kiloampere, which gives the factor of 2.41 between the RMS and the peak. Normally we have the factor of 1.414 for the peak and the RMS, but here you can see it is 2.41. Now how this value will change, I will show you. Now I am making the fault current occur at the 90°. 90°, but basically here I will do 89°. So you can see 89°, what changes. Now this is 46, this is 46, this is 112. I'm changing this to 89, and you can see this remains 47, but this is from 112. It's changed to 60 kiloampere. Now the peak, you can see it's changed to 60 kiloampere when the fault occurs on the peak of the voltage point on the wave. Okay, so this is the first case. So what we are doing is we are talking about the duties at zero voltage, but in reality it can be a less, too much lesser to that. Okay, the second point that I'm going to explain you is what is the effect of X by R. Now I'll make it worse again here, 0, and we'll change X by R. What will happen the X by R if I change the X by R? Now suppose instead of 8, I am having X by R of, let's say, 4.9, which is the ideal case for a testing circuit by IC, which will result in a power factor of 0.2. Now, if you see, the RMS has not changed. The total current is still 47, but the peak has reduced to 112. From 112, it reduced to 104. And the multiplying factor, you can see, this is 2.21. Here, maximum we can go, let's say 0.01. What will happen? You can see, and now this is almost, and the transient is not there almost. Okay, so this kind of now when we have X by R is equal to 1, at the power factor of 0.7, the circuit is 0.7, means it is most likely an inductive motor. So induction motor will have this kind of a nature when we start any induction motor. Now we'll see. Now this is one particular DR that is actually real time short circuit that is taken from the relay. You can see the asymmetry here. So this was in one of our client. This event occurred where there was a short circuit recorded, and this is the waveform taken from the relay. So if you can definitely see here, the DC component is there. The asymmetry is really clearly visible here. So actual condition also we get this kind of waveforms. So this is not only limited to some sort of calculations, but in reality we have this kind of waveforms on the field. Okay, the third question which everyone must be having in mind, why this transient component, where this DC basically component comes from, because we are not giving any DC current, DC voltage, we are not having any DC component in voltage. Then how does this DC voltage DC current comes from? So basically this is basically common to everywhere. It is common to even the capacitor. When we switch on the capacitor, initially there is a high inrush current. When we switch on the motor, then we are having a high inrush current, and all these inrush current will have this DC component present. So where this DC component conceptual wise I will be explaining, but before that, as we know, in this formula of solving the differential equation, we already know this is present, but this is a completely a mathematical solution of the circuit. But conceptual wise, what is exactly the IT that we have to see, or we must know what is it? So if you see, when I start any motor, or let's say for this matter, there is a short circuit. The short circuit will have the impedances from the sources. So it will have some X, and it will have some R. So at this moment, as this circuit will be of a lagging nature, right? So at t 0 plus, it should be going forward, or it should be have the maximum current. But at t minus 0, if you look before the fault, the current is 0. So as you know the nature of, this particular circuit, this will not allow, the inductor will not allow the change in the current. So if you see, it will have to develop some sort of induced EMF to comply to the Lenz's law. So on this particular instant, it will draw exactly opposite but of equal magnitude the transient current. So this current is drawn from the source, and it will keep on drawing till the time it reaches to its actual value in the circuit. So this is basically why transient component is here. If you see into this is the induced EMF that is required to be very high. And if you see the rate of change of current here at the initial, it will be very high. So obviously it has to induce a very high voltage. But how it can do? It can only do that by drawing a heavy current from this source. So with this, we are will be just going forward into this, because I know this quite looks boring, and definitely you can approach us if you want to understand this in detail. Okay, we'll just move a little to the next slide. Okay, this before this, let's understand these terms through waveform. Again, this is we are taken these definitions. We know what is this, but now we'll see on the waveform how does it looks like. What is initial symmetrical short circuit current is. So the same arrangement here, the same graph. So here you can see uh, this particular from A to C. This is basically what we call it as a ICM, that is a making peak. So manufacturer has to give this value for ICM compliance. Okay, and then there is a ICU, right? ICU and ICS. I'll explain you what is the difference between this. But let's say for a matter of understanding this, ICU is again, as we know, this is a breaking current. Now let's say fault has occurred here, and now fault is opening at this particular time. Okay, so now our fault is opening means breaker is opening, the breaker contacts are getting opened, and there is an arc in between this. Then this E and F is basically measured by IEC. They measured the exact component of this, and they do a simple maths here, that whatever the EF will be there divided by 2 root 2. 2 root 2 I'm saying because they normally take, because this is envelope, this is a complete envelope. They draw a complete envelope of DC component. Now this component, my drawing is bit okay, so this will be component. So this is complete stuff, complete value they will be taking, because they have the oscilloscope. So they measure this complete magnitude, and they do 2 by root 2, and to get the IB, that is RMS breaking. So RMS value they have to come across, or to check for the compliance. So this is basically ICU and ICS. So on this waveform, this is the value. Now there is also one aspect which nobody is actually talking, IDC, that is DC current. So DC capability of the circuit breaker. So this particular wave, this DC component gives the IDC. So at this moment, this is the IDC for this. At this moment, this is the IDC for this. So if you see the definition, the definition says this is the mean value of these 2 points. IDC means the mean value of these 2 points. So they take these 2 points, and take a mean out of it and do the average, and they calculate the IDC for the circuit breaker. So this is the explanation for these terms. I hope I am not missing on any term to explain. IB, I have explained IB, I have explained I peak, I have explained IDC, right?
Yes.
Okay. Now let's see the next poll. Now,
I think they have already probably learned the difference.
Yeah.
And then
Yeah.
they've already given them the answer.
Yeah,
if I'm
right,
not
right.
wrong. So yes, I think most of you would be now aware of the difference between IC and ICS and ICU with Prasad's deep dive into the waveforms.
Yeah.
We
So
can go to the next.
poll.
I guess. Maybe we can, yeah.
Yeah. So the difference I'll be telling in the next slide. So difference lies in, again, as I told you, ICS, ICU, manufacturer has to decide. There is a hard and fast rule. But the IC test requirement is this. For ICU, the IC test requirement is OTCO. Means O means circuit breaker is in open condition. Then there is a time gap of not less than 3 minutes. And then there is a one sequence of operation, close and open. So the fault circuit is already there. So this circuit is already there. And you have circuit breaker. Now you have a circuit breaker, you have to close it and immediately you have to open it. And after this test of sequence, then physical verification of the breaker is done. And if there is no physical damage to the breaker, then ICU is passed. Okay. Now ICS is the test sequence where there is a OTCO, TCO means closing and opening occurs first, then there is some time gap, and again there is a closing and opening on a short circuit. So this is basically a repeated test that has been carried out. So ICS, basically the difference is ICS value is given for a repeated short circuits. So breaker has to withstand to a repeated short circuit for this particular value, that is ICS. Whereas ICU is only a one-time test. After one time fault clearing, if the breaker obviously there should be no damage, but for that breaker it is not expected to again put into the service. But if ICS, your fault current is less than ICS, then your breaker is expected to take into the operation or bring back into the service again. Then there is a ICW, withstand capacity. Open T, and between the close and open operation, there is some time gap. There will be some time gap. So if the breaker manufacturer says 50 kiloampere for 5.5 seconds, then for this value there will be hold, no tripping of the breaker occurs, and then there is an opening of the breaker. So after this test, again the breaker is checked, and if there is no damage on the breaker, then ICW is passed. So that is basically the difference between the ICS and ICU. Okay, now let's talk about the ICW. ICW, I think most of these studies, people are not considering ICW at all. They are only concerned for my breaker is 50 kiloampere, my short circuit level at fault or at bus is 45 kiloampere, less than 50 kiloampere. They say it is passed and we move forward and the device duty is clear. But this ICW is actually important factor that should be included in the device duty reports. Okay, so ICW, as I said, the breaker manufacturer, let's say here in this example, 25 kiloampere for 3 seconds withstand. If someone is, some manufacturer is claiming for, then 25 kiloampere will pass for 3 seconds, and then there will be no damage in the breaker contacts, no damage into the insulation of the breakers. Small fittings are allowed, but no major damage is allowed in this test. So this is basically the ICW. ITH is quite different than ICW, but in ETAP you can see the people showing you the ITH value to compare the ICW. So basically the ITH value, what we see in 60909 is different, and the ICW value is different. In IC 60909, the ITH value is nothing but some factors MNA and I double dash K. So this comes from these values. This is thermal, basically thermal capacity. Whereas the ICW take care of the thermal stresses as well as the mechanical stresses. So there is a difference, but in ETAP, people, you can see these values are given in this relation only. So okay, you all must have know that a breaker we say 25 kiloampere 3 seconds. So does this allow more than 25 kiloamperes for 1 second? What would be your answer for this? Okay, poll is display. Yeah. So what do you think? 25 kiloampere 3 seconds if stand is there, but I have a breaker which can clear in 1 second. So can we have more than a 25 kiloampere?
I mean, you have a fault.
Fault, yeah. So let's say my breaker manufacturer says 25 kiloampere is 3 seconds by ICW, but unfortunately I have selected a breaker of lesser capacity. The fault at this particular bus is, let's say, 35 kiloampere, but my breaker manufacturer says that we are clearing the fault in 1 second only. We are not waiting for 3 seconds. Okay, so can I pass this breaker for 35 kiloampere then? The poll.
Okay, so there's almost 50% upside yes. You can.
Yeah, basically yes, because this is completely depends on I square T value. So it is inversely proportional. So the T lesser T, we can go for a higher ampere. But basically, if you see the IEC standard or IC testing, basically, so manufacturer will give 3 to 4 different figures for this. It is not completely blindly based on I square T value. It will have 35 kiloampere, for example, it will specify for 0.5 second, 40 kiloampere, it will specify for 0.1 second. So 3-4 values manufacturer will give, and then IC will test those values, and then only it will confirm the compliance with ICW. So it is not basically, you cannot actually go and calculate the I square T formula, make I square T, make a constant and apply for this. That would be not the proper way of doing it. Okay, so
I think we can now do suspense and.
Okay, so now again the same graph and the same breaker that we are explaining, we showed earlier. This is the 630 breaker, this is the 400 breaker. We run the device duty, and the result says the thermal energy. You must have seen in your SCCS reports, you open any of your SCC reports, these figures will not be there. The device duty comparison on thermal energy, nobody does or nobody asks for. But basically, you must be asking for this particular device duty compliance. So here in these two breakers, these breakers, if you see the capacity, I will run to the next slide. The capacity and the fault current here is 45 kiloampere. but still it is showing failed. Now these breakers are 50 kiloampere rated. So I'll show you the next slide. Here you can see this breaker, which is 400 ampere one. Here you can see the ultimate breaking capacity is 50 kiloampere. Service breaking is 50 kiloampere. My fault is 45 kiloampere. My fault is 45 kiloampere, but still in device duty, it is failing. Because if you see the short time withstand here is only 5 kiloampere for 1 second. This is given by the manufacturer. This is particularly the NSX breaker. And why I'm saying the coordination was wrong, because, and I said earlier also that the breaker itself is not allowing to enable or disable the instantaneous value. So this instantaneous was not able to be disabled from breakers. But you can see the consultant, the coordination engineers will be submitting you this kind of graph, and they will be telling you that the coordination and the selectivity is done and it is proper. But this is not the case. This instantaneous, if you can see, the breaker current is 4800. So after 4800, this breaker, if you see the withstand capacity itself is 5 kiloampere. So after 48 kiloampere, 4.8 kiloampere, it is not expected to withstand for 0.1 second or 0.4 second. It is not expected, or it is not the capacity of the breaker. So instantaneous disablement of instantaneous in this particular case will break your breaker when there will be a fault. You may achieve the selectivity, but on the network, if the fault occurs, this breaker is going to be get damaged, and there will be no starting it again. So you will be losing the complete line of this breaker. Same this thing, because once we have the NSX in the downstream, upstream, we normally take the same manufacturer, same, everything is same. So here you can see short time withstand is 7.56. Now you can see the difference. The short time withstand is just 7 kiloamperes, but this breaker is guaranteeing for 50 kiloampere opening and making of a 105. So you can see how much difference is there. I've seen the consultant saying, even the manufacturer saying that you take ICW equal to ICU. In many cases, I've seen when there is no proper documents presented, people say you consider ICU equal to ICW and you make a report and submit. But ICU in a real scenario is different. Here also, it will not allow the instantaneous. The maximum tripping or maximum instantaneous will be limited to less than 7.5. In this case, it is just 6930 kiloampere, 6930 ampere, which is 6.9 kiloampere. So this is the reason where we said this coordination is wrong, because it has to have the instantaneous region overlapped on each other. Because if you see the difference, earlier it was 4800 ampere and here it is 69000. So definitely this both breaker will trip simultaneously on any fault more than 6000 or 4800 ampere, and not 4000, 6900 ampere. So we have taken the screenshot from Schneider website to explain you where actually, to what extent ECPL goes and check the documentation. So here in Schneider website, they have clearly mentioned we have no ICW for value for NSX up to 630 ampere. So up to 630 ampere, all this breaker has to be tripped on instantaneous. So these devices have a utilization that is a different category. We normally go for category B, where we have to disable the instantaneous. So this level, we have to go and check the conditions at the site before we submit the TCC.
And hence, for the case that we said, the only answer is to replace the
breakers. Here, there will be no other options by retrofitting some ETU trip unit. Some may will give you the suggestion that you replace the ETU, or you replace the tripping uh, circuit, or you replace, or you put some external bypass. Yeah, so that you have to avoid that. For that, this was the webinar basically. So with this, we are looking forward to for a next session of this webinar.
So I think there are some questions we can take. So there is a question where Mr. Jagdish has a 400 ampere breaker connected to 16 motors, and with one motor having 16 ampere, he is requesting what is the setting for IR short circuit and instantaneous.
Okay, but that basically the question of everyone, when we are having multiple loads connected and we have one breaker feeding to multiple motors or multiple loads. Basically, that breaker is not expected to protect the motor. That breaker is basically for the protection of the cable or the bus bar of that particular panel. It is not for a protection of that motor. Motor has its own protection. Motor will have its thermal overload relay. It will have its own MCCB or fuses. So that is primary. But the backup you cannot set to 16 ampere, and which is not expected basically. So we always say for that particular case, you have to see what is the largest component that we want to protect, or which is the primary protection required from this breaker. So for this breaker, primary protection would be the bus bar and the cables. I have answered your question. That will be actually covering up into the next presentations, where we'll be talking about the protection device coordination only.
Yeah, we'll deep dive into the actual coordination settings, and now that we have established the foundation, so there's one more question. Do change in frequency in the range of plus or minus 1 hertz will cause larger impacts on coordination, assuming on DG power to utility power? I don't think there is any impact of frequency.
So frequency impact on a settings, you are saying?
Yeah, I think on the coordination basically.
The coordination, see, basically when you change the frequency, obviously some of the factors may change, but from the utility only we have the plus 1% tolerance is given for a 99% of the time, and I think for 100% time it is 4%.
Yeah, so this is comparing the utility versus DG. I think the bigger worry which should be the impedance and the characteristic of the source, which will play a bigger role in coordination, as opposed to frequency, which typically in DG you will have 47 to 52 hertz. I think that's the range.
But that is a source dependent.
Yeah, that's source dependent. So, Shikant, if you want to ask any questions. Yes. Okay. Mr. Jagdish is asking about I need what we said breaker setting 400 ampere breaker for the 16 motors. What settings do we set on the 400 ampere breaker?
You can set it to the maximum. You can set it to the bus bar capacity of the panel. That's it. So the primary protection would be bus bar, not the motors.
Yeah.
Mr. Vivek Parman has raised his hand.
Yeah, you can allow him to speak. Yeah. Yes, Vivek ji, you can please go ahead. Meanwhile, we have one more question. Can a higher interrupting capacity breaker fail at lower fault magnitude in practical real world case?
Can.
Can it?
Yeah, it can fail, definitely, because it is a component. It can fail on anything because the failure is not is dependent on the insulation, how you maintain the breaker. So I think your question, I am not understanding it very well, but you are saying if it is in service and if it is
Lower
getting a
capacity
damage,
fault, yeah,
yeah.
a lower
Yeah,
interruption.
that is possible because
There are other factors.
yeah, there is other factors. So temperature is there, moisture is there. So basically insulation fails. Yeah, but this gives me another one point which I actually missed. This device duties basically is for the through fault. It is not for the fault on the component. So when you are saying the fault occurs between the poles of the breaker, then it has nothing to do with the ICU or ICS because the fault has already occurred on the insulation. So the basic concept of these ratings is for through faults. It is not for the fault on the component.
Right. Okay, so we have the next question. How we take care of selectivity during design line or giving order to the panel vendor? I think a very important, very pertinent question.
Yeah, but for this, what exactly you are expecting?
So basically, what should be done to ensure selectivity during the design stage? I guess the one part is a design consultant needs to be very sensitized with respect to selection of the devices and have this consciousness about device duty selections, about limitations of device duty based on different breaker makes and models and their characteristics. Like we showed you, right, the Schneider.
Yeah.
is a limitation.
The best part would be you accompany a team like ECPL along with the design consultant so that everything is coordinated, well coordinated.
Yeah, because there is no other alternative than to work in parallel with a number of iterations along with the design team. So a lot of projects where we work with the design team, and there are iterations which keep going on to select the right switchgear, raise flags much well in advance. It is, I would say, iterative process. It is a time consuming process. But if it started much early on in the design life cycle of any facility, the results in terms of replacement of breakers later on, in terms of miscoordination, in terms of failures occurring, etc., can be highly reduced. So I hope that.
Good question.
Huh?
That was a good,
Yeah.
good question because we have seen number of cases. We have seen now the client is will have to change the breakers.
Yes.
They have to implement certain logics, interlocks to avoid the contingencies. So a lot of things happen after the design.
And I think once again, thanks for the question, Viveki, because if at all our purpose of this session was actually, the question that you raised, to create awareness about why short circuit and device duty plays a very important role during the design stage, and it becomes a very, very costly affair if it has not been addressed appropriately earlier on.
Because you can talk about one case where the device duty selection was higher, but
Yes.
the actual fault was quite much lower. Yeah, because if you go for a breaker selection of from 25 kiloampere to 80 kiloampere, the cost is huge.
Huge, yes, yes. So we'll cover more case studies in the subsequent sessions. Okay, I think Jagdish, you can probably speak if you want to. We can allow you to speak. You are unmuted right now. You can go ahead and. So we can take that offline, Jagdish. You can mail across to us your particular case, and then we can deep dive into that. In the meanwhile, I'll request the participants to please help with your feedback. It will really help us to improve anything on the content, to make it more engaging, to make it more relevant to you. But as I said earlier, the risk we run is, of being very trivial, very superficial, of which knowledge can be easily available from Google or some research papers, versus bringing practical insights and linking them to theory. It is a tightrope walk, and hence at times practical industry people may find it difficult to. Yes, Vivek, you can, if you have raised your hand just now, you please go ahead and speak. You are unmuted. Okay, hello. Yes.
Right. Yeah. Am I audible?
Yes, yes, yes.
Question is same ki this selectivity, how we will taken care selectivity in the design. And then already maybe you have given the answer and discuss because my side network too. That's why I miss.
Oh, okay. So,
Yeah.
so we, I mean, one is we will obviously be sharing the recording to you also. But what
Okay.
we said is that the only best alternative to that is to have an iterative process with during the design stage, working to identify the limitations, if at all any, of device duties, of various switchgear that you're going to be selecting, and running through the short circuit calculations, running through the protective device selectivity, simulations during the design stage itself, and not leave it later on once everything has been finalized and then doing it on the field. It will result into definitely, either requiring replacements or retrofits or all of those issues. So that's why we have started working. I mean, not started right now. I would say we've been doing that, but not every client is ready to indulge in these studies along with the design consultants or their own design teams much early on. So because a timeline is always premium in data centers.
Yeah. 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 Yeah.
So, but you have seen it, in your projects also you have seen that one
Yeah.
or two.
Yeah. That's why I asked because I face issue on my two of three sides, same issue.
Right.
So
So earlier on that we start working on these, simulations and device duty appropriateness of your design, the better it will be in allowing to even before you are actually going for tendering and you are going for selecting of your makes and models, it will be
okay.
allowing you to do that.
Okay. Okay. Okay.
We're
Thank you.
actually
Thank you.
doing some consultant right
Yeah,
now.
we are doing that with some consultants where we have defined, 2 or 3 iterations as part of the whole studies to take care of this thing itself.
Basically, the focus was on short circuit
Short,
device duty.
right, device.
Okay. 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 Thank you.
Thank you, thank you. So I think thank you everyone for joining once again, and thank you Sachinji for your comment. Means a lot. It's the students, I guess, who are going to be the next generation, and the more they understand these topics in detail, the more our power systems will be more safer and reliable. So thank you all for joining. We will continue and keep you posted on the next sessions in the series.